Good evening, everyone, and good morning to some of the friends who are joining from Nepal. Um, Today, this talk would be mainly focused on the recent Nobel Prize in Physics that was awarded to John Hoffield and Jeffrey Hinton, and we'll be talking briefly about what kind of research were they doing, which was related to artificial intelligence and neural networks, and the second part of the talk where Dr. Kamal Dhakal would be talking about the applications of the things that they have developed during their tenure and how it has been applied in different kind of research presently. So brief outline is that on the first part of the talk, I'll be talking about what is a neural network, how does it learn, how is it kind of similar to the human brain, how has it been designed to look like similar to a human brain. Then I'll be talking a little bit about what is a Hoffield network and what he did at that time, the paper that awarded him the Nobel Prize. And for the application parts, Dr. Dhakal will be talking more about it. So basically, neural networks are a set of algorithms that are designed such that it can recognize different kind of patterns that we supply to them. It would basically what it will do is when we supply some information to that network, it will grab some of the information out of it, pull the most important information, save it in its memory, and when somebody asks it, hey, what is this? It will just basically tell you what it would be based on the memory it has stored during it. So the function of the neural networks in artificial intelligence is similar to the function that a neuron does in our brain. And we'll talk about what kind of similarity we see structurally between a neuron that is present in our brain versus the neurons that we talk about in terms of artificial neural network. So in this slide here, what I'm trying to show is a simple set of neural network architecture that is being used in artificial intelligence and many machine learning models. There are three important layers in any neural network. The first layer is the input layer, where we give them information. The hidden layer are in between layer. In this picture, the blue circles. I've only shown one hidden layer, but it can have like a lot of these blue rows on it. It can have a lot of those kind of hidden networks in between. And then finally, what you'd have is something called the output layer. So three different sections: input layer, where you feed the information for the machine to learn or remember or memorize the information that we provide. The hidden layer is where all the calculation happens. It tries to store the memory, and then output layer is where, based on the memory stored and based on the inputs that we supply to the machine, it will tell you what it should look like. For example, if you want to, let's say, create a machine learning model using artificial neural network, you can supply an image of cat as an input. And in the hidden layer, it will do bunch of calculation and it will store a memory with different numbers. And if it sees another image of a cat, it will basically come close to the same number that it was stored before. And on the output, it will say, hey, this is the picture of the cat. That's how it kind of functions. Now, I would like to, since most of us are physics majors here, and people have been talking about neural network and all of them say it's a black box. We don't know what's going on inside. That's not true. Actually, we know what goes on inside. The calculation is very easy, but it happens so many times in such a big network that people don't try to get in and try to understand what's going on. So what I'll be trying in the first part of this talk today is trying to make people understand how neural network works. In this case, I'm trying to create a neural network, a machine learning model, where I've got this table over here. I've got 4 different persons, Ram, Sam, and Hari. And let's say in a day, they play, like Ram plays for 2 hours, studies for 8 hours, and sleep for 12 hours. And based on those information, result is the column where I've got a bunch of ones and zeros, where 1 means the guy passed the exam, let's say, and 0 means the guy failed the exam. So I'm trying to create a model where I am supplying the model with the information from three different guys, Ram, Sam, and Aryan, how many hours they played, how many hours they studied, and how many hours they slept per day. And based on that information, whether they passed or failed, so 1 means the guy passed, 0 means the guy failed. And based on this information, what I would like my model to do is I've got the fourth guy, Manoj, down here, and I'm saying the model that he played for 5 hours, he studies 3 hours, and he sleeps for 12 hours. Will this guy pass or fail the exam? So this is kind of a very typical, simple example of the problem that we are trying to solve right now. And the way a network is designed, the way a neural network is designed is in the input layer that I had shown in the previous slide, we pass the inputs, or in terms of simple geometry or linear geometry, linear algebra concept, we are just passing, these are our x variables, play, study, and sleep is all our x. So we put x1, x2, and x3, three different variables, and y is our output. And in this case, we know the output of three, or the result for three different persons. And I'm assuming that it is a linear function. Sorry, it's a linear function of the form y equal to mx plus c. So basically what happens in neural network is when we supply those numbers, let's say if I'm talking about RAM, then this number is 2, this is 8, this is 12, and we have got this W1, W2, and W3. These are called weights. These weights are at the beginning of the simulation or at the beginning of the programming, we supply a random number for the weight. Let's assume all of them are 1, W1, W2, W3, and W4. These are the weights. And the bias term, or in this in the geometry, we usually call it the intercept, but in machine learning we call it a bias term. Let's say we have got bias as well. So what happens is this number will go in. So a 2 and a 8 and a 12, they all go in, they add up to 22. And then when they add up to 22, because we have got W1, W2, W3 all as one, they simply add up, right? So we'll get a 22. And then it goes through this something called activation function. We use it because we know that not all the problems that we want to solve are linear problems. We can have quadratic, we can have exponential functions. So sigmoid function basically non-linearizes the problem, so that even if you have a second degree or third degree dependence on x and y, the model can learn that quickly. And in this case, we have got this sigmoid function, which is of the form 1 by 1 plus e minus z, e to the power minus z. And what this function does is, does not matter what number is being supplied as an input to the sigmoid function, the value of the output will always lie between 0 and 1. So if you give it a high negative, it will be close to 0, and then it will get some intermediate numbers. And even if you start giving it a high positive value, it will kind of give you a 1. So this kind of sigmoid function kind of makes sure that whatever number you are getting out of this is between 0 and 1. It has got multiple benefits. For example, like number one, if there is non-linear pattern, it helps to catch those kind of patterns as well. And number two, it helps to ease the computation, because if you are multiplying, like let's say million times million, that it takes a lot of space. But if you restrict everything between 0 and 1, that's a very few bytes that you have to work on. So it makes your life easy. So it passes through this sigmoid function, which is our, in this case, where all the calculation happens. So this is our hidden layer. And then finally, based on this, it will again multiply with this weight W4 and goes through another sigmoid function. It might or might not, it doesn't matter at this point. And it will give you a final number, let's say y hat. So basically what's happening here, we are randomly assigning the value of the weights at the beginning of the simulation. We know x1, x2, and x3. It goes through a sigmoid function, and then it gives you a result. And in this case, y hat is our predicted result. Now, for example, let's say it did all these and we got y hat equals 0.1. So if you look at the previous slide, for RAM, whose number was 2, 8, and 12, the result was 1. So we are expected to get 1 at the end of this entire calculation. But let's assume we got a 0.1. So at this point where this is the point where the second Nobel Prize, which was given to Hinton, the second person, his concept of feedback comes back on onto the play. So at this point, what is happening is your model has learned, but your model is really bad because you wanted a 1 over here for RAM for 2, 8, and 12. We wanted 1, but we got 0.1. And so what do we do in order to fix this is we want to devise a method which would somehow go back into the whole calculation. It will kind of traverse back. That's why we call it a feedback. We will hold traverse back the entire sequence in the reverse order and try to figure out what are the good values for W1, W2, W3, and W4, which are called the weights. So we want to find the optimum value of weights, W1, W2, and W3, such that we get 1 for our Y. So in this case, the loss is 0.81 because we wanted a 1, which is the real value. We got a 0.1, which is the predicted number we are getting right now. So we've got an error of around 80%, which is really bad. This is a huge loss, and we are trying to reduce this. There are different methods of reducing this loss, and one of the common ways is by using the concept of gradient descent. In machine learning, we call this optimizer, and gradient descent is something of a concept that we are all familiar with. So what Hinton did was kind of use this concept of going back in that entire neural network and fixing or calculating the new value of weights based on the previous value of weight and the error it gave when we use that value of weight. So in this case, since our error was like around 80%, what it does is it goes back and does this math where it says, hey, my error was really bad. So what I will do is I will have the old weight, I will multiply it by a constant factor alpha, which is called the learning rate. I'll talk about it in a while. And what is the rate of change of my loss with respect to that variable W4? So it would basically calculate that difference and then update it weights. And based on this new weight, it will do the exact same calculation and then start propagating backward in order to update the values of W1, W2, and W3, the new W1, W2, and W3. So what is happening here basically in case of the loss function, which was of the form y minus y bar square, is can be seen in this small diagram about the gradient descent. So if you look at this picture, we have got a function fx equals x squared minus 4x plus 3, which we want to find the minima for this. And the way to do it is the way the the neural network works is it just picks a random weight, right? For example, I picked 1 on all of the numbers. And let's assume that point where W1, W2, W3, and W4 all were 1 was this red dot. And just looking at this curve, we know that this is not the point of minima. The minima is down. So how do you find a minima for any function? Is you do the derivative and you just find the slope at that point. And based on the direction of the slope, if the slope is going in the negative direction, you would basically say, hey, it's going in the negative direction, so I want to go down or I want to go up. You want to take steps towards the point where the value of the function will be minimum in this case. So that's where this alpha comes. Alpha is called the learning rate, and this is the size of the step. For example, if there's a red dot, if I started from that point and my step was each of these arrows, like 1, 2, 3, 4. In this case, I'm taking 4 steps, and alpha would be the size of that step. So alpha is kind of a variable that we would have to decide on what the number you'd want to put it there. And these kind of numbers that we have to tune in order to find the minima are called hyperparameters in terms of machine learning. So basically what happens here is it is taking one step, calculating a new W new, and then again calculating the error. So at the first round, it was 0.81. Maybe in the second round, it became, let's say, 0.6. And then it says, hey, it's still bad. And then it takes another step and then tries to calculate the error there. And maybe it came down to 0.4 and we still think it's not good. And so you keep on taking the steps, appropriate steps, until you find a minimum. So again, just like I said before, alpha is a parameter that we supply. We say how we tell them what would be the size of our step in order to find, and we have to be very careful on what would be the size of our step. Because if the size of your step was big, let's say your size of stepwise from here to here, like I had 4 steps over here, but if this was 1 step, then the next step that it would have taken is the red dot would have moved at this point, and then it would have kind of overshooted the minima and it would have gone somewhere there. So what would have happened is that your loss would be kind of oscillating between these 2 points and never finding the right minima. So the choice of alpha becomes very important. Similarly, how many times do we want to do that? Like how many times do we have to come down in order to find the minima is also a hyperparameter, which basically means that you have to be smart enough. You have to do bunch of experiments in order to figure out what is the right size of your step and also what is the right number of times you'd want to perform this calculation so that you will find the minima. And also, this is a very simple function, right? It just has a one minima, but there are functions which has a lot of global minima as well as local minima. In that case, the problem becomes more complicated, but we're not talking about that. We're just trying to understand how neural network works in this case. So basically what we do in a neural network is we update our weight, calculate the loss again. If we don't like it, we go for another round, calculate the loss. We don't like it, we go for another round. We don't like it, we go for another round until a point comes where it says that, oh yeah, if it's wrong, then I'm going to get a 1. So if the width at the end of this simulation, the result would be that you'll get the value of W1, W2, W3, and W4 in this equation, so that you will get a 1 when you plug those numbers into this function. So that would be the ultimate goal. Obviously, you'll never get a 1 because it's a probabilistic thing. You'll get a 0.9, but you can always round it up to 0.1. You can define your threshold. You can say if it's more than 80%, then only, let's say, he passed. If the probability is less than 80%, I will say the guy is failed. So you can determine the boundary. You can decide your boundary on where to say that, okay, if the model is 80% sure that he's passed, then only I'll call it a pass. Or you can say, I can put the threshold at 50-50 by default. He just does 50-50. Anything below 50% would be fail. Anything above 50% would be pass. But basically, you have the freedom of deciding the threshold as well. So, so this is how a neural network works. The first step is the forward propagation, where we assign the weights. Everything moves forward, and then we get a big error. And then we start moving backward, which is called the back propagation. And that's where Hinton comes in. Jeffrey Hinton comes in, who kind of use this concept of back propagation in neural network so that you can update your weights at each and every step and make a good model out of it. Before Hinton, the neural network was still there in the market of artificial intelligence, but they didn't have the concept of back propagation. So it kind of froze for like 10 or 15 years. The neural network never progressed. The progress of neural network did not happen until the back propagation was introduced into the whole AI scenario. And from that point is when everything started booming up. Then there came a point where our computers didn't had enough memory to run, and then the concept of GPUs and everything started adding up after that point. So, so basically, this is a very simple yet elegant example that how a neural network works. And yes, it might be a black box if you don't want to dig in and see how it works. But if you really dig in, spend some time on it, there's a math involved in it, and it's a very simple math. First order derivative is not a problem for anyone who is attending this meeting. So so what happened here, let's look at a slightly different picture. I created a model where I gave information about Ram, Syam, Hari, and based on that, I created a model. And at the end, I will give this model a 5, 3, and 12 in order to predict what Manu's results would look like. And based on the weights that this system has calculated before using forward and back propagation, a bunch of them, a bunch of backs and forths, it will multiply with the weight. It will go through the activation function and it will give me a result over there. Now, the accuracy of the model depends on a lot of factors like the learning rate, the number of times you did back and forth, and also how many of these inputs were supplied to you. Usually for a good model, you want a lot of Ramsam and Hari type of entries. That means you want a lot of entries where we can tell the machine what the result should look like. So the more information you give to the machine, the better the model it creates. So this is how typically a modern neural network works. Now, I will jump into Hopfield network, which is also a neural network, but it's way different than the forward and back propagation kind of network. In that Hopfield network is trying to mimic our brain more than it is trying to do with the artificial neural network. The artificial neural network, the model that I built about predicting the result, is also a type of neural network. Again, the concept is same. It is basically neurons connecting with each other and sharing the memory, sharing the bits, sharing the results or weights in this case, and then trying to see which number fits. But in Hopfield network, it kind of does the same, but it's slightly different in the sense that it has no back propagation. That means the things are not going back, like I talked about before, that the thing that Hinton used in neural network. And it is more biologically inspired, and it is based on the concept of one shot experience. So in the previous network, as I said, we wanted a lot of Ramsam and Hari to be supplied into the model. We wanted things that we know, a lot of them for the machine to learn. But in case of Hopfield network, it doesn't work that way. It is trying to mimic our brain in such a way. For example, in our brain, usually when we see a picture, we remember it. We don't need to see like thousands of pictures in order to memorize something. And this is what Hopfield network was trying to do, the network that Hopfield created. So you just give it a one sample instead of Ramsam and Hari and bunch of other people that I gave in my previous example. In this case, I just have to give it one sample. And based on that, it will basically remember it and tries to, and if you give that model some other things to recognize, it will go inside, calculate it and see whether it is similar to the pattern it had remembered before. And so that's why it's called a one shot experiment. There are no back and forth, there are no training sets. So so let's see how it works. In this diagram, I am showing 5 neurons that creates a Hopfield network. Each of the neurons are connected to each other, and all of them should be connected with each other, and the weight between the first neuron and second neuron is same as the weight between the second and the first neuron. So it is bidirectional, and there is no self connection, meaning one neuron is not connected to itself. It is only connected to the remaining other neurons. So and this network, the Hopfield network, is also called associative network because it kind of relies on the concept of association. It says by association, it basically means it looks at the surrounding and sees, based on the surrounding that is associated with it, it will try to decide what the prediction should look like. So couple of problems that was there with Hopfield field is that Hopfield net is very memory. It takes a lot of memory to remember big things. For example, if you have n number of neurons in your circuit, in your neural network, it can only remember 0.15 times the number of neuron patterns. So if you have 100 neurons, it can only remember 14 to 15 patterns most, and after that point it kind of starts to hallucinate, and the model will kind of go crazy. So that's why Hopfield network was not that reliable back in the days. There are much more advances that is done to it. There are different techniques added on top of it to make it better, but the problem still exists. Now, compare Hopfield network with something like other neural network that people are most frequently using. For example, like Chat GPT, right? Chat GPT 3, I don't know about 4, which is the latest, but on Chat GPT 3, um, I think it had around 175 billion neurons. So think how massive that model is with 175 billion neurons. Compare that with human brain, and I think human brain has around like 90 billion neurons. So the number of neurons in ChatGPT is more than that of human brain, but human brain is too complex. We still don't understand a lot of things that happens in our brain. And So ChatGPT is not as good as our brain, but we're talking about the simple model, the Ramsam Hari thing that I showed at the beginning of this talk. It's based on that thing. It has got input, it has got bunch of hidden layers, and it has got output layers. And the design is, I just wanted to talk about the massiveness of ChatGPTs and all those models that are currently in the market. So coming back to Hofeld, this is a simple network with 5 neurons, and you can see they are all connected with each other. And on the right, you can is a kind of a circuit diagram of how they are connected and how the information is intersected between them. So Hopfield network is again based on how the neurons in the brain functions. So there is a concept where if you study neurons, you will be really familiar with it, where it says that if the neurons that fire together, they are wired together, and neurons that are out of sync fail to link. So this is the very basic concept of Hopfield network, and it is even based on even simpler function that the weight between any two neuron AI and AJ is just simply equal to the product of the values stored by that neuron. So in the previous example, if two of the neurons have value of 1 and 1, your W23 and W32 in this case would be equal to 1. And if they are plus and minus, it will be equal to like -1. So positive is basically attracting. That means similar neuron, they fire together. And if they are plus and minus, then they are kind of repelling each other, or they're not firing together. And this is similar to brain in the sense that previous research on neurons have shown that if the action potential, which is basically the amount of energy given to a neuron to activate it, the action potential is similar, then the neurons that have similar action potentials, they will fire together. But if two neurons that have like slightly dissimilar action potential patterns, they will fire, but at some point they will slowly, the connection between them slowly start to decay, and at the end it will kind of degrade and maybe even die after certain time. So exactly the same concept is being used in the Hopfield network. So let's see how it works. A very simple example. In this case, I'm creating a Hopfield network with 25 neurons. So basically, these will be like 25 neurons that all are connected with each other, except it is not connected to itself. And I am giving it a structure of a T. And this is what I fed to all that 25 neurons. So this is a 5 by 5 grid of 25 neurons. And so in this case, this will be 1, 1, right? 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. Those neurons will have a value of 1. And even these neurons will have a value of 1. And everything white would have a value of 0. So that's how I kind of initialize my table. So So that is how the Hofield network will remember the pattern that I submitted it to remember, and I'm only submitting it one time, unlike the previous example of Ramsam and Hari, where I had to supply information for multiple people so that the model can train well. In this case, in contrast to that, I'm just sending one sample, and that sample will basically work. Now, when I give that T shape to that 5 by 525 neurons of Hopefield network, it will remember it, and it will basically create this giant matrix. And you can see the diagonal element is all 0. That's because the neuron is never connected to itself. Now let's see how this works. I'm not going to go through math because of the lack of time, but remember we started with 25 neurons, 5 by 5 grid, and I gave it a shape of a T. Now we want to see how it predicts. In this case, I am giving this pattern on the left where it kind of looks like this on the left. And based on this, I want this model to understand that it is a T, or will it say it's a T or not. So the way the machine works is based on this, it will start calculating the weight of the nearest neighbor. For example, the weight was basically very simple, right? It was just the product of the AI and ages. That means the ith neuron, the value on the ith neuron and value of the jth neuron. In this case, all my blue is 1, all my white is -1. And the way inference work is it will pick one point, and then basically it will pick a point in the grid and see whether that value is correct or not. In this case, I have got this red square over here. And what the model will do, what the Hopefield network will do, is it will start calculating the weight of this square. So it will do a multiplication, sum of the multiplication that you see over here, Wij, and then calculate what would be the total sum. Like in this case, white times white is -1 times -1, which is +1. So this is +1, this is -1, this two will be +1, between these two will be -1, so on and so forth. So it will do all those multiplications, sum it up. And if the value of the total weight comes out to be positive, then it will say, hey, this would have been a plus, but it's minus. So what it will do is it will flip it as, so this red square, if you do a calculation, the weight will come out to be 19, and 19 is greater than +1. So what the Hopefield network does is it flips this white to blue. Now, similarly, the process happens for all of these boxes. And ultimately, it will reach that point where it will recognize that it was very similar to the pattern of T. And it will say, hey, it looks like T. Now, this is a very simple example that I showed. And in this case, it was 25 neurons. So 0.15 times 25 would be like 3 or 4. So the maximum number of patterns it can remember at a time for this 25 neuron network is 3 or maximum 4. So maybe you can supply a T, you can supply a P or a R, but if you start sending it more than 3 or 4 patterns, it starts to hallucinate because it will find multiple local and global minimas, and it would fail to decide whether it should be a blue square or it should be a white square. At that point, it kind of fails to recognize the pattern, and that kind of became the biggest limitations because currently ChatGPT and all other models, they are very efficient in terms of memory. It can remember a lot of things, and it can also generate information even if it's not fully occupied in the memory, and collect it and put it together. So this is basically a very brief introduction to Hopefield network, what he did, how he worked on it, and what was the kind of concepts that he utilized so that you can remember the pattern. And Hopefield network is famous in the sense that it exactly mimics our brain. For example, even for our brain, we don't need a lot of examples or a lot of incidents in order to remember something, right? For example, like if you hear a huge tire screech on the road followed by a bang, you know it's an accident, and you don't have to uh, have that incident like 100 times until you know it's an accident, because it's the concept of association, and Hofield network is also a kind of associative memory. It will basically look at, hey, I hear a screech, I hear a bang, and maybe I hear an ambulance, there's an accident. So that's kind of association. You're collecting number of informations in between, so those are firing the right neurons at the right time with right potential, and your brain is remembering that thing. And Hofield network is exactly the same. It just gets one time, for the first time when you hear the screech, the bang, and the sirens, that's where you store the whole information in different part of your brain, saying, hey, this is the part where all this information are stored. And the next time when you hear the similar event, and even when you only hear part of the event, just the screech and the bang, even before you hear a siren, you automatically know that it's an accident. That's what associative memory means. And that's what it did. We started out with a T, which we recorded it. And then in the next part, what I did was, instead of that T, I gave kind of a broken T. And even based on this broken T, once it starts calculating weight on each and every point of this grid, it will finally recognize that it's a T, and it will say it's a T. That's what kind of Hinton did with his associative network for the paper for which he got the Nobel Prize. So this is the thing from 1975, I believe, for Hinton, and there has been a lot of work after that. And in order to talk about all those works and how those are applied currently in different part of the research, I would like to welcome Dr. Kamal Dakal and enlighten us with that part. Thank you.
All right. Thank you, Dr. Sri Bhadrai, for this nice introduction. I need your help to, move the slide forward. Okay, let's go from the beginning. I think we have limited time. I don't like to go more details. Is that the first issue, right? Yeah. Okay, since I am working mostly in the neuroscience, ophthalmology, and somehow in a little bit in the, I feel also more talks about the, already Siri explained a lot about how memory works. But one thing is, as I said, he mentioned most of our classical AI, what you have been listening most of the time says, you need a large set of training data. For example, if you like to identify dog, you have to give bunch of dog images. And if you like to identify cat, you have to train on the cat also. But in this, after the development, this Hochschild network, what we call in the classical term, it is a attention network also people call, similar like as brain. For example, right now you don't have to remember anything, almost looks like brain empty, but if you see something else, then for example, if I see somewhere like one of my old car, then I can remember my like my past places, like wherever I study, that goes on. A lot of those information comes into your mind, even though at the moment I don't have anything. So what is that driving is called attention. That's why that network or pull network is called attention, because as Siri mentioned, most of those neural network, they are feed forward. The one layer passes to the other information, but in the Hochschild network, there is a each one passes to there is a self loop, one neuron connected to each other, right? So that creates the attention. So, and then the idea is, like the memory, it is a story into the different types. If you like to learn neuroscience, mostly there is a explicit memory, implicit memory, and like some of the things we don't have to control, even like the movement. If I like to walk, I don't have to think how to move my legs, but there are some other which you have to you have to decide yourself. But this is the memory what that is associative memory is kind of long-term memory where we associate with, we store, and it is really interesting. If you go to the next slide, I think most of the stories is stored in the hippocampus. But now that part is very nice. If you like to look at the after this talk, if you go and look at into the Google, there is a lot of PBS, I think documentary about is how that even we know how that hippocampus store the memory is very fascinating story. One of the patient nowadays they call Mr. HM, shortcut HM, but Henry Gustav. Actually, that dude in around 1953, he was in 25 years old, and he was constantly getting the epilepsy, and he was seizure. Your life was messed up. At the idea the cause of his epilepsy or the seizure is he somehow had his he fell down somewhere and there is a head injury at the childhood, but he didn't realize. But after as a 25, he got that severe epilepsy around the time when he was 25, 26, and his life getting very worse. And he went to a doctor. By that time, even the neuroscience, the medical research was very not that well developed. Whether it is for the research, whether the doctor has to even do some investigative research or not. And there was a nice doctor, William Scoville, at the Hartford in Connecticut, right, in Hartford Hospital in 1953. He offered, okay, if he, I mean, just by his guess, that was not even known that time. If you take out your hippocampus, probably that the memory you are getting, that epileptic, he think that he gets some types of memory and he gets faint. He said, okay, if you do that surgery, if I can remove your hippocampus, probably you won't get that epilepsy, that seizure. And actually, he did that surgery. This is the real image of his brain, still stored in the lab. And then, luckily, now that his seizure is lost. I mean, he didn't get the seizure. But the one good thing, I mean, one good or bad thing, that he will never he'll never remember the new memory. He'll never form the new memory, but he still can remember the past, but he'll never form the new memory. So that proves, okay, hippocampus is the place where new memory is formed. But where is his store? Like there is a different story. And from his brain, there is a lot of neuroscientists, like even see the Wilder Penfield is a very famous neuropsychologist, which is she studies his brain. So that is the idea. That's why that memory formation start from the real neuroscience experiment. Next slide. Just like to give you some interesting things. Then now you see this is the one simple the paper that they got new Nobel Prize in the physics. Many people in this audience, including myself, may be wondering, well, why that is in the physics. What is really, is there anything like temperature, viscosity? We are familiar with physics. Is there anything at the beginning? All these neuro computational work number matrices, which is nothing to do with physics, right? But there is some formula. If you read this paper very nicely, for example, let's suppose this is a memory attention. How does it work, right? Memory is stored in different part of the brain. Similarly, how you code in mathematics is this is let's suppose there is a this Xi1, Xi2, Xi3, Xi4. There are 4 times of memory. But how that network? How do you recall Xi1, Xi2, Xi3? In the discrete form, very basic form is similarly like as you have to apply gradient descent, and then you minimize, and then what they have in the next slide. Siri, I don't like to go more detail because I think I have limited time. Siri, go to the next slide. If you look at their formula, that energy, what they encoded actually that state the associative memory in the form of energy, which looks like more physics, right? If you look at this their formula. And then sigma Tj is a tensor matrix which you can you can construct from that memory attention. That Xi I. If you look at that, then you might have infinite memory like a chat GPT. How much parameter he has? The chat GPT, current chat GPT 3 has 175 billion parameter, means that many networks, that many things he has to remember. So that is a multi-dimensional energy storage system, if you can, in terms of physics. And then you have to minimize. The previous example is that if you minimize, the stable memory is forms when the energy is minimum. So as in similarly idea in the physics, and the only problem in this hopeful network is like you have to find out that value of k, as Siri has mentioned. Sometimes it does not. If you give more than 3 or 4, it just confuses. It does not converge. Only careful approach you have to choose is the right parameter, that value of k, where the network will be converged, right? So after development, this associative network, what you call hopeful network, right now they call dense associative memory network. You can even make it continuous by just derivating this. Then what is the advantage? What is the advantage is in the standard generative transfer block like a chat GPT, right? Any standard transfer network is, unlike the neural network, transfer network learn from the one eye. For example, if you train on dog, it stores some part of the image, some part of the information, and then if you give the cat, somehow it remember the dog is that and cat is that, so it transfer the knowledge. Actually, like is like our human systems, like so many people have done so many research. That research is transferred to me. Similar like the in this network, neural network, the knowledge is transferred from one learned parameter to other parameter, which is not possible into the classical neural network. And after introducing this generative network, this is called transformer block. This is the backbone of the chat GPT. That's why it's called GPT, generative pre-trained model, right? Generative transformer block is look like this. But if you add the full network in between, then what it creates is, then it associates the memory. So it not only predict randomly, then it can remember the previous memory and interpret it is more PCL. That's why if you look at ChatGPT 3 and ChatGPT previous version, well, if you tell them to write long paragraph, it will just divert, it will not converse. Nowadays it is very well written, right? Based upon that associative network. So go to the next slide, because I don't like to deal more in math. So now the example is, like I work last year a little bit on my research, but unfortunately I could not share due to the confidential data. There is some of the things I put it there. Most of the times, well, most of the neural network, they while using images, and I have been doing a lot of this image processing in my career also. That's why, for example, if you train like hundreds of parameter, anything like if possible in the life, uh, and then in later in your time, it is very helpful in the medical term. I don't know how I can explain here. For example, if you have the eye images, if you have the x-ray, which is very poor, sometimes the image is not right, sometimes the quality is not right. So what does that this hopeful network does, it if you train that, if it already knows what the eye looks like, what the bone looks like, then if even if it has a bad, like for example this input data, if you give it, it predicts exactly the output, what would output looks like. So if there is a missing, sometimes even in the MRI field, if you go to the MRI in the brain, there is a lot of variation that the image contrast was bad. Even the little bit more liquid, sometimes the people whatever they eat, if there is a something imbalance in the image contrast, we don't need to now depends upon the machine. Like if the machine is not higher resolution, or we can reconstruct those poor images. So that is the one of the example in the hopeful network can understand, or even if you give the very little bit information, it can reconstruct the image. Go to the next one. And then but sometimes what it does, it not only reconstruct, if you give the piece of this, like as the Sri has shown, what they call in the generative model, they call token, right? In the ChatGPT also, any other model. So in those images, you divide it into number of pixels, maybe 25 by 25, hundreds of hundreds. And what it does, it actually, let's suppose if there is a tiger in somewhere in the grass, the real image, then you divide into, let's suppose if, for example, here is the four pixel or four token, I would say. But if you have many like large images, large size images, you can divide into 100 by 100 also. So then what that hopeful network does, it creates so many tokens in this example is a four, and then it goes into the iteration and minimize the energy where the minimum energy is. First of all, where that token is, where is its position also spatial position, like left, right, or the coordinate in terms of matrix. And then from the previous like is memory, previous associative memory, then it reconstruct the image like this. Pretty sometimes it's not perfect, but it is the good image. You can get it from even the partial image you give it. So that is the beauty of this energy transfer block, or that or pull network. This is the recently paper in 2023. They have explained very well that whole the hopeful network. Similar like here, like you can divide into the, if you like to find out the dog or not, you see, even if you give the very less noisy, like nothing even you can identify by human, if you give the some pattern on it, because the background of this whole network is a lot of matrices, right? From this pattern, it can remember the images. Then you have to, it is a time evolution network, you have to repeat over the time and time, and it gets better and then predict the very well images. Go to the next. And similar, this is the reconstruction. This is the one of the example from their paper, which is published last year. I put it. As you see, one of the problem here is how do you choose this the weight what Siri was calling, or in case of this hopeful network, the error or that value of k on that previous formula. If you choose right those parameter, you can really from these random patterns. There is nothing in the first place. If you look at the first row of image, no one even can think of there is some meaningful image. But over the iteration with using this transfer learning means it has learned from the previous patterns, some those patterns, it can create this exactly what it's supposed to be, beautiful images, which it's supposed to be. So that is the example. You can see one of the best example in real life. Next. Yeah, this is the final slide I like to talk about, which is my research also. But this is the last. Let's look at the first example. If you look, if you see there the image, it is using the hopeful network. There is a GitHub also. If you look at, I can even share that link. It can, with this very noisy data, it can create the real image of the person. Now, how that is helpful, right? You know, one of the example I've been using this on my. That's why I even when Sunita approached me, I said I'll yes, because only thing where I applied is that retinal tissue identification. You know, I'm working as you see, I'm working on the ophthalmology field. Most of the times we image the retina. Our eye has uh, 10 different layers in that small 0.5 millimeter thickness of our retina back of our eye. They have 10 layers, and these 10 layers do so much computational and send the information to the brain. And most of the types of glaucoma, like as the one of the eye, which you'll get it. Many people are got blind by this disease when get older in old days. The hallmark of that disease is one of the layer, like we call the RNFL layer. There are 10 layers, which is not even visible on these images, that get thinner and thinner. The neurons get died. And most of the times when you image, you know, like again, sometimes the image, the light is more bright, the intensity is more bright, the image is not good quality. So you won't always expect the best image in the world, right? There is even most of the times these images taken by the simple technician, they don't know even any mechanism of the image acquisition, right? They simply click the button. So that also impairs the clarity of the image. Using this hopeful network, you can really reconstruct the nice images, and you can use that as your research or investigation or any other tool. And recently, I forget to put it here because if you look at, there are one of the Google paper they have in 2020, I think 2018, they published that one of the first AI doctor. Means if you present the eye image, the fundus image, you can really early detect whether that person will have glaucoma or diabetic retinopathy or like any macular degeneration. Those types of disease you can identify from that patterns, though they have trained a lot of images. But the point is, it can associate those memory and it can predict a disease which even the doctor cannot see it. That types of patterns the network will understand, and they have been using mostly in the ophthalmology. They are really using this that network primarily for disease detection. And this one nice paper which they have used, like multidisciplinary or 3D open network on this paper, where they have shown, okay, why don't we do reverse? And that is also case. For example, nowadays the privacy, the privacy is very important factor. And how do you even if the person goes hospital, all of those images are in research. How do you um, encrypt them? How people won't know their real name or information, right? So if you can construct that from that noisy, like these types of image to this beautiful image, why not then even the X-ray, this beautiful image, denoise and save as a pattern? For example, if the chest X-ray of the person save in this pattern, which computer can understand and later can reconstruct, then you can save those images. Even no one can even read their name or like it is a more encrypted form of. So reverse engineering, I would say, either you can reconstruct from the noisy data to make a nice image and use this as a disease detection, or in the reverse way also, you can save those images as a noisy image so that no one can even understand, no one can even read it what that it is, just for privacy. I think that is we were almost an hour. So that's the application in a brief. And thank you for your attention.
All right. Thank you very much, Dr. Sri Bhattrai and Dr. Kamal Dagal. I really appreciate your time and accepting our request to give us the talk about Nobel Prize in Physics and its theoretical aspect and the application. I think the floor is open for any questions from the audience. Please unmute yourself and then you can ask your question.
Hello, I have a question for Dr. Sivatrai. So, could you go back to the slide where we had a linear cost function for the RAM SAM model? Yeah. So, what will we do to find the cost function if we do not know which order of polynomial do we have there in our model? That is my question.
Actually, you never know what kind of model it is, whether it's linear or not. It's the neural network that will decide based on the weights. And usually, until you go and dig into the weights, you would not even know whether it's a linear model, quadratic model, or something like that. The when you do like a number of iterations, the weight itself will kind of tell you what kind of model is it. Basically, you cannot go back and construct an equation looking at the weights that you get from a neural network. That's why most of the people try to call it a black box, because you cannot like come back and feed on it. But something you can do is you can always do a plot before you feed it to the model. And sometimes you can see it to be a combination of a second order or a third order equation or a combination of those, and give that equation as one of the inputs to your model so that your model can learn better. But there's no way for you to know whether the model is linear or quadratic unless you already know from empirical equations or something, like from some equations in physics or something like that. But the loss function is always second order. That is used to is always in a square, and it's usually always positive. It's always positive because if you have a positive and negative loss, you can have a situation where your positive and negative sums out to be zero. You think the model is perfect, but actually it would be a terrible model. So loss is always positive and hence always a square.
Thank you.
Hello. I have a question about using half-field model for image detection. First of all, very, very nice talk by both of the speakers. Anyone can answer this question, I think, both of you. So how is this half-field network for image detection different from the convolutional neural network in terms of computational efficiency? Can you elaborate on that, please?
So there are pros and cons to both the method. For example, in terms of the CNNs, the convolution neural networks, you need a lot of cat diagrams in order for the model to know it's a cat. You might want thousands of pictures of cats, thousands of pictures of dogs, right? To be fed into the model before the model recognizes. If you just give it a one cat and a one dog, you will build a terrible model out of it. It's not going to work. And not even that, even what like most of the times when we play with image, we just not only provide an image of the cat, but I usually even rotate the image of that cat by like 5 degrees and like build, I don't know, like 150 different images of the same cat, because you might not always get a cat which is standing up, right? So if it's a cat falling down from the sky, you still want to know it's a cat, and you don't want to train a model where it understands that when both the feet is on the ground, that's only the time it is cat. So for CNNs, that's the problem. You have to have a large amount of inputs. But half-field network, you don't. You just need one image. Just like in one of the slides that Kamal sir shared, this is your train data, this is a dog. That's it. You just supply one model. It remembers the pixel around it. It assigns weight to the pixels around it. And based on the association or attention that each pixel is getting and the input data that you provided, it will kind of try to resolve each and every pixel in this diagram and try to reconstruct what it had remembered before. So you just need one sample, one input for which you want to get a prediction, and this is the output you got. So it has got both pros and cons. Like if, for example, the IE image that Kamal sir talked about, there is one layer with a beautiful picture, perfect picture. You train on that, and every time you get a bad image, you just apply it to the off-field network. It will kind of resolve itself and get you a better pixel diagrams. That's the main difference, and you would want to choose one network over the other based on the nature of your problem.
So you just need one training example to train your Hopfield network.
Yes.
Less data set,
then
and also it can transfer the knowledge, like if you have, for example, if you try to, let's suppose, identify the war of two different species, right? The parrot or maybe other crow. Like these birds have pretty much 80% similarities. And then the network will remember from the previous location, somebody has trained the crow. You don't have to always give hundreds of crow and hundreds of parrot. It will remember like all the similarities from the previous train or previous patterns and apply those training with that new, if you, for example, provide the parrot, right? So that's the one of the things that it also transfer knowledge. And then really things is like if you have billions of parameter like a ChatGPT, how the good example is ChatGPT, and there is a attention also where you put the attention, that will more get power. This is more get activated, and the probabilities goes more there.
Okay, thank you. So we should not be using CNN at all then, right?
Well,
image detection.
depends
This is the
upon
way to
what
go
you,
actually.
Depends
So, I
on
mean,
depends
yeah.
on your problem.
yeah, depends upon your problem.
Yeah. Okay. Thank you for the answer.
Yes, thank you for the nice talk. Just I want to add, like what happen if the image is rotated or shifted, those things that I think in that case we need the CNNs.
I mean, usually you do the data augmentation before you do the any like training, right? Data augmentation means like you rotate, flip, all those kinds of directions. Usually we do for before training the data.
Yeah, you can even use attention Hopfield network for that. For example, like it's like this formula over here, 0.14 times n. You can have, like, if you have 100 networks, then you can pretty much see 14 images, right? So you can rotate your image 14 times and give it there, and it will ultimately pick it up. But I would not go to that extreme limit to do this. You might want to stay with fewer number of patterns fed into the model so that it does not get confused.
And what about if you have the generative models, then that means we have the transfer of knowledge there. So,
Right.
but you mentioned that the Hopfield models has the transfer of knowledge, how it comes from there.
Hopefully has attention on the transfer is, you're right. Like you don't need a hopeful network just for transfer network, right? You can transfer the knowledge, but remember then how many billions of parameter you should have if you, well, sorry, the billions of parameter you will have it, but for example, if you write in the ChatGPT, you see ChatGPT, every word is a prediction. It looks like, okay, it's writing like an essay for us, but every word, what is the every last word is the prediction of the previous word. So then how does it knows that which is the right word is based upon that attention what that awful network is provide. Wherever that more attention goes, those parameters get activated, and the most probably those word will be selected.
Isn't that comes from that Boltzmann distributions? That if you
Boltzmann. Also, I forget to mention the Boltzmann's got the Nobel Prize. One of the reason is because also the back propagation, but also he, based upon his theory, there is a Boltzmann machine, right? Which is the
yes.
statistics model, but that is from the random data, right? You can also include that. That's why I think that is also included in the ChatGPT model. I don't know, but Boltzmann usually from the stochastic, like if there is a random data unsupervised learning, then you use a Boltzmann machine.
Yes, thank you so much.
So I have another question as well. So I heard people say kind of a trade-off between bias and variance in machine learning, which I don't quite understand. Could you help me understand the concepts?
I think we'll keep that to our ANPA machine learning programming, because I don't think I'll be able to explain you in like 1 or 2 minutes at this point.
Thank you.
Any other questions from the audience?
I have one question.
Please go ahead.
Nice talk, guys. That was great. Thank you very much, Dr. Bhattrai and Dr. Kamal Dhakal and Dr. Sri Bhattrai. So my question was about the weights that we were talking about. For example, when we are looking at model fitting and determining the parameters. So it looks like there could be multiple, right? Like degenerate solutions for a single problem. Is there a way? Because it seems like the models really do not matter. What matters is what the predictions are made out. And sometimes complex model may perform better than the simple model, sometimes because you're tuning out the parameter. Is there a mechanism to encourage simpler models? Because I think that would make the life of everybody simple, when you can fit the same data by using simple linear model, why bother with the, non-linear, non-parametric models?
That's a very good point. Like usually people who wants to go in data science or even learn anything, they start with AI and neural network. I've been working in data science job for like last 3 years, and I have not even written a single line of code on neural network because we don't need it. Like we are not building ChatGPT. Most of the problems that we have in our day-to-day life in our business are very simple: linear regression, XGBoost, tree-based models. Most of the times, like even if you look at Kaggle, which is a place for competitive data science projects, the model that has been used the most and has been the winner is tree-based model like XGBoost and light ZVM and things like that. So we don't need neural network. Neural network is for problems that are too complicated for classical models to solve. And even when I deal with any modeling, my first go is linear regression. If I can solve with that, then why would I need a neural network? We don't need it.
Exactly, same true.
And it's the other important thing is, especially for people like us, if you go to your boss and say, hey, I fit this model and I think we can increase our sale by 15%. The next question your boss would ask is, what if we close this store? And if you want to answer that, then the only way to answer that question is linear fit, because linear fit is where you like turn off one of the parameter and see how it varies your result, right? And you can actually tell the number. You can say, hey, if we close the store, then our sale will go up by 3% or 2%. Or if we color our store red from red to blue, that might be aesthetically pleasing and more people will come in. But if you want to put a number on by what percent changing any of those variables will affect your output, then you can't use neural network at that point. It will just tell you the final result, but it won't be able to tell you what are the intermediate contribution of each of those different parameters in your model. And you basically come back to linear regression. So yeah, like sometimes I would say most of the times all these AIs are a oversell.
I was about to tell same story, like most of the times, these people, or if you include somewhere AI, the people think, oh, is smart, okay, good thing. But if you do simple thing, people think, oh, this is a basic. Same thing like image processing. I think Naveen, you might be also aware of this reconstruction image you can do by simple paper and salt noise, like Gaussian noise. There are so much image processing model even before like this AI things in I don't know how many people are here in computer vision field. Like I've been using image processing for a lot of time, and I never used this AI before MATLAB, like image, all those were able to segment, identify those images. But the problem is now if you don't use AI or if you do simple, sometimes people think like if you include somehow AI, people think fancy. But I think we were buying a machine gun to kill a mosquito in some cases. This is and also if your data is not large, like large data set, you're wasting a lot of time and resources just to train to get one result from the 10 images. That's not helpful at all.
Yeah,
If you have
it's like
hundreds
buying
of
a
thousands of images,
AK-47.
right? Thousands and 47, like thousands of images, and you have routine job every day. You have to run thousand images. You cannot do by manual, or you cannot do selecting ROI or doing manually. At that case, might be helpful, but it's what it is nowadays. Sometimes it is really kind of fashion in the market.
So sorry to interrupt, Dr. Kamalji. Do you use Hopfield network in your work, or you also don't use
I
this
have, that's why I
for
use
image processing?
during the learning time, I use it sometimes in some of the
No,
cases.
day-to-day work.
Well,
Day-to-day
day to
work.
day, as I said, these days, I don't know, guys. Nobody writes single code. Everything we have the proprietary software which is inbuilt. All these neural network inside. You just dump the data there, hit the run, train, done. I don't write single code. What is inside? I don't even care, honestly.
So,
Everything is
so
inbuilt. Too easy.
nowadays you can buy all those
Thanks for
models
the
like
honesty.
yeah,
Yeah,
you can buy commercial packages like that, right? If you are working in industry, you can buy those
right,
packages online, and there are so many people who develop it. We don't even question. We
right.
just run it.
If you are engineer, if you try to modify a network, like create a new network, then you probably have to understand all those theory. But these days, everything is inbuilt inside this proprietary network. Either you're using Google platform or IBM platform or anything else. CNN is inbuilt. Opal network is inbuilt. Like whatever, therefore, random forest is inbuilt. You just select the model, hit the train. That's it. All right, guys, it's really. I know we both are working for a AI field, but that Opal network is not that. Oh, we have to do every day, but we think okay, at least we can understand what it is mean. That's why we decided to shed some light on it. I don't know how much it will be helpful or not, but at least why it was physics is because of this Boltzmann statistics and some kind of this energy function. Otherwise, I don't think it's supposed to. I don't know, whatever they decide is decided, but there is not much physics behind it.
No, it was a great talk, and thanks for the giving us the combined effect, the effort here. I really appreciate that. And then in a short period of time, I do apologize that we request you guys very lately, and not enough time to prepare all these model. I see how much work Sri has done to prepare this slide. I can see that running those, and same thing for Kamalji. Really appreciate that. Yeah, I think we still have 2 more minutes. If anybody has a question, please unmute yourself, and then we can wrap up the talk.